All right, well, welcome to the end of week 2. Holy crap, that means we're a sixth of the way done with this quarter already. Seems like we just started. Today's plan, I definitely want to show you more substitution. Substitution is a great method for integrating and is going to allow us to get some functions, some integrals of functions that we know, but we don't know how to anti-differentiate yet. So that's what my plan is. But as always, I'm happy to go over a couple of homework questions if anybody's got them. Would we like to look at anything? Suzanne, I probably will not do all 3 of those, but I'll put them on the list. So she's like,
if you want to choose one, I would do 14. I think I needed the most help with 14.
Okay, so we've got 8, 12, and 14 on 1.4. Anything else? Alexi seconds your vote for number 12. All right, well, let's go take a look at those and see what they look like. So I'll go ahead and share my screen. So I'm pretty much already ready for this. So we'll pull up 1.4, give it a second. All right, so I told you guys I like to have good, bad jokes while we're wasting time. Anyone have a good, bad joke to share here while we're waiting? Make sure it's clean.
I have one.
All right, go for it.
How can you tell that a tree is a dogwood tree? By its bark.
Oh, wow. Tim coming on strong. I like it. All right. That's a total dad joke. I am definitely putting that into my repertoire. All right. I'm going to go ahead and jump to number 12. Let's see what that guy looks like. Okay, so number 12 says, suppose that a particle moves along a straight line with a velocity of 12 minus 5t, where t is between 0 and 1/2. So the velocity is in meters per second, and clearly the time is seconds. So then find a formula for the displacement of the particle and the total distance it has traveled at time 0.5 seconds. All right, so.
Wait, this is the wrong homework. It's 1.5.
Oh, you wanted 12 from 1.5.
Oh, yeah. Substitution.
Okay, that's all good. Because this was one of the ones Susanna asked me about. But real quick, so this one, let's just talk it through real fast. How do you get displacement from velocity? I didn't talk about it. Well, in this class, but you should have picked it up in Math 105. How do you get position or displacement from velocity?
Antiderivative.
Yeah, it's the antiderivative, right? If we've got a position function, you differentiate, you get velocity. You differentiate again, you get acceleration. So if you want to go the other direction, you anti-differentiate. So acceleration, you anti-differentiate to get velocity, anti-differentiate velocity to get position. So this one, we just have to anti-differentiate. You're going to get a plus c, but you can use the plus c, or you can get the value for c by realizing that at time 0, it hasn't moved anywhere. So it's an initial value. So that'll get you your function. And then if you want to get your total distance traveled, you just plug in 0.5. So I'm not going to do that one, but that's the process. Real quick for 8. This is exactly the same story, except you're given acceleration. So you're going to anti-differentiate acceleration to get velocity. And then you're going to anti-differentiate velocity to get displacement. And again, they give you some information here, right? They give you your initial velocity is minus 8 meters per second. And you can know that the displacement at 0 is 0 because it hasn't gone anywhere yet. So those two are both pretty similar. Let's see if 14 is along the same lines, then we'll just do that one and call it good as our example. Oh, no. Okay, 14 though. Let's look at 14. Somebody popped into office hour yesterday and asked me about this one as well. So we've got a woman who's walking on the treadmill, and what we've got here is an amount of calories that she's burning, given by 300 minus 5t. All right, now is that actually an accurate function to represent how much calorie expenditure you have while walking on a treadmill? Probably not. Right? Probably not. It's probably not decreasing as time goes on, but we're going to just go with this. That's what the computer gave us. But then it also says that she's bringing in calories. She's got caloric intake from drinking Gatorade, and that's at 125 calories per hour. Right, so she's drinking Gatorade. Again, is this a good function for how many calories she's taking in with Gatorade? Probably not. What this is saying, if you look at that 125 the caloric intake is increasing with time. So that would mean she's drinking more Gatorade as time goes on, which might be true, right? She's exercising, she's sweating a bit, she wants to drink more Gatorade, but I have a feeling that that's probably kind of a ridiculous number. But that's all right, we'll still go ahead and figure this out. And so it says, what is her net decrease in calories after walking for 2 hours? So basically, we want to know after 2 hours, what's going on with calories. All right, so I'm going to switch to the whiteboard in just 1 second, but let's first just think about this. What are we going to do to find out the number of calories that she's actually expending or taking in? What are we going to do with these two functions?
Plug in 2 for t.
We're eventually going to want to plug in 2 for t. If we plug in 2 for t right now, all that's going to tell us is how many calories are being expended at that point in time, right? So like if you plugged in 2 right now, you'd get 300 and minus 100, which is 200. And that's saying that she's burning 200 calories per hour, because this function is telling us a rate of calorie expenditure, right? And then this 125t, that's the rate of calorie gain. So if we want to go from a rate to the actual amount, how do you get an actual amount from a rate? Or how is a rate related to an actual amount? There you go, Adam just put in there, you take an antiderivative, right? So we are going to want to anti-differentiate. These are rates. Look at the units. It says calories per hour. So if we want to get calories, we have to anti-differentiate with respect to time. We have to integrate with respect to time. And so Era's also put in there, you know, combine. We are going to want to combine them. We're going to want to look at the decrease in calories from working out, but then the increase in calories from drinking the Gatorade, and see how that balances out. So we definitely do need to combine them. Adam said, add them together. I don't like add. I think we need to subtract them, right? If you think about the expenditure, that's a negative. The intake is a positive. So one's going to be positive and one's going to be negative. So it's, I guess it's technically adding, but we have to think about one of them as a decrease. Oh, if you meant the summation to get us the antiderivative, then yeah, that definitely is what's going on. Okay, so let's jump to the whiteboard again, and I will show you how we can do this. All right, so I'm going to just do the two separately. I'm going to look at the calorie loss. So the caloric loss. And this one, we are going to anti-differentiate from zero, or integrate from 0 to 2. The 300 minus 5t dt. So this was how she was losing her calories. And I'm going to integrate from 0 to 2 because we're going from now to 2 hours from now. Because remember, that's what integrals do. They add stuff up. So this is adding up all the calorie expenditure over those 2 hours. All right, so let's anti-differentiate. The 300 gives us 300t. Gotta love anti-differentiating constants. The minus 5t is going to give us a minus 5t squared over 2. We increase the exponent by 1 and divide by that value, and the 5 was a constant multiple. All right, so now we need to evaluate those at 0 and 2. So when we plug in 2, we're going to get 600 minus 5 times 2 squared over 2, which is 10. And then when I plug in 0, both of those things are 0. So we get 600 minus 10 minus 0, which is 590. So over those 2 hours, she actually loses or uses 590 calories running on the treadmill. All right, so how are we doing so far? Good with that? So now let's look at the gain. How much does she actually gain? Well, she gains it by chugging the Gatorade. So we're going to do exactly the same thing as before. We just have a different function, right? She's taking in calories at a rate of 125t. But if she does that over the 2 hours, we're going to add it up over that entire time interval. So the antiderivative here is going to be 125t squared over 2, going from 0 to 2. All right, so you plug in the 2. 2 squared is 4, divided by 2 is 2. 2 times 125 is 250. And then when we plug in 0, of course, we get 0. So that's the fundamental theorem of calculus, right? That's the f of b minus f of a, right? Same thing over here. So over those 2 hours, she burns 590 calories and she takes in 250 calories from the Gatorade. So what's her net loss? How many calories?
290.
All right, so Adams put 340. Mariola said, I think it was 290. Well, it's going to be 590 minus 250, right? We're going to look at the difference of those,
340.
which is 340. It's all good. Okay, so the answer to this question is net, she loses 340 calories. So this is the process. This is how I would do it. Just take my loss and my gain and then find the difference. We could have done it just as a single integral if we wanted, right? The rules of integration say that the two separate ones can be combined. So we could have done an integral of 300 minus 5t minus 125t, right? And that would have given us the same thing. All right, so hopefully that makes you feel a little bit better, Susanna. And at least my talking about the other ones, how to get positions from accelerations and velocity, hopefully that kind of reminds you what you did last quarter. Okay, so the other one that we wanted to look at, Alexa, you said that was, remind me, number 12 from 1.5. Yeah, okay. So let's go back and find that guy. All right, so this is probably going to take a little bit. Who's got another bad joke? Although that one to Tim's is going to be hard to eclipse. That was definitely a groaner.
What do you call a watch? I mean, a belt with a watch on it.
What do you call a bat with a watch on?
A belt.
Oh, a belt with a watch on it. No idea.
A waste of time.
Oh, man. We got some top-notch ones today. I like it. Oh, come on, computer. I've been having the weirdest technical issues the last couple days. Like all of a sudden my phone, it's connecting to the internet, but I'm not getting Facebook messages from my wife randomly. You have weird power fluctuations happening. I'm telling you, it's end of days, folks, end of days.
I work from home, and I noticed that Fridays are the worst when it comes to connection. I think it's the amount of people in Tahoe. I know you're not in Tahoe, but
we'll use that as an excuse. I like that though. Yeah, I don't think down here in the valley the numbers of people have significantly increased, but I wouldn't be surprised if you're actually correct about that, Mariola, because there's probably a pretty decent influx, and there's only so much bandwidth, right? Okay, finally, we're here. All right, so again, evaluate this indefinite integral. So maybe a little bit different than yours exactly, Alexi, but it should follow the same kind of idea. You're shaking your head like it's not even close.
Mine is just asking what the local max is, so it has nothing to do with that.
Really? Are you sure you're looking at number 12?
I'll look.
Because they should all be fairly similar.
Oh, that was my bad. It was on 1.3.
Okay.
You don't have to go back to it. I can just ask after class.
Okay. If you want to find a local max, how do you find a local max? Just in general. Go back to first year calc. What do you do to find a local max? Can anyone help out here? How do you find maxima and minima? What do you do?
First, we want to find the critical points.
Okay, so you find the critical points. So you take the first derivative and you set it equal to 0. And you also set it, see where it's undefined, and those are your critical points, right? And then you can test to see if it's a maximum by looking at, is my function going from increasing to decreasing? So that's the first derivative test, or you can use concavity, look at the second derivative and see if it's positive or negative. So depending upon what the function is or how we're creating the function, we might need to get to the derivative in a different way, but it all comes down to where is the derivative equal to 0 or undefined. So start there and then test it. So see if that helps. If that's not enough of a push, send me a message and we'll get together sometime and chat about it a little bit more. Okay, so we are down to a little over 15 minutes of class, but I do definitely want to show you a few more substitutions. So I'm actually not going to hop up to my whiteboard. I'm going to save ourselves some time and just show you stuff directly from this whiteboard. But just want to remind you real quick about the whole idea of substitution. Substitution, what we're doing is we're turning it into a form that we know how to integrate, right? Like, for example, let's say we were looking at the integral from 1 to 5 of x over the square root of 2x minus 1. And you look at that and you go, wow, I have no idea how to do this. This doesn't look like any function's derivative that I know. But we recognize that having a square root, if it's just the square root of u, t, something like that, we might have a shot. So what we're going to do is let's try a substitution. We're going to plug in here. I'm going to pick u. That's kind of my go-to. And I'm going to let u equal 2x minus 1. Because I've got a shot if I do this. All right, now that means that I'm going to get the square root of u down here on the bottom, but I need also to replace my dx. So here's where we differentiate. We're going to differentiate both sides of this, and that's going to give us du equals 2 dx. So the whole trick here was, you may remember when we did it the long way, we wrote du dx equals the derivative, and then we multiply by the dx. I just saved myself the time. I just differentiate and then multiply by dx. Okay, so this tells me that dx is going to equal du over 2. So I can start replacing stuff in this integral. I now have the square root of 2x minus 1 as the square root of u. My dx, well, that's du over 2. So the only thing I have left that I need to replace is the x, right? I got to take care of this guy. So do you remember how we did this? What's the trick to solving this for x? Or substituting for x? All right, yeah, so we're going to use the substitution. Thanks, Stephanie. We've got this u equals 2x minus 1. So if I just do some algebra on that, I get that x is equal to u plus 1 over 2. So this substitution is key. It lets us do everything. It let us find the du and the dx so that we can replace dx, but we can also use it to replace our x's. So there now is everything in terms of u. We'll do some algebra to simplify that in a second. But there's still one more thing we have to do, which is change our bounds. So I'm going to go ahead and change our bounds right now. The same substitution. We're going to look at what happens to the, what do the u's become when x's are 1 and 5. So if x is 1, we get u is equal to 2 times 1 minus 1, which is 2 minus 1 or 1. And then when x is 5, do the same thing, and we get 9. So the bounds on this thing, when we switch it over to u, is going to be from 1 to 9. So everything in there is now in terms of u. And let's see what happens once we simplify this. So I'm going to get a 1/4. I've got u plus 1 over the square root of u. I just pulled those constants out front. And while this one may not look super nice, it's actually going to be really easy once we do some rules of exponents. We're dividing by u to the 1/2. So u over u to the 1/2 is going to give us u to the 1/2. 1 over u to the 1/2 gives us u to the minus 1/2. So the calculus was done right here to allow us to change it. Then we did a whole bunch of algebra, but now we're ready to do calculus again. All right, so let's get our antiderivative. U to the 1/2, it's a power rule, so we're going to add 1 to the exponent. Gives me u to the 3/2. And then I'm going to divide by 3/2. The other piece, do the same thing. I'm going to get u to the 1/2, because minus 1/2 plus 1/2, or plus 1 is 1/2, divided by 1/2. And we still need to evaluate this at 1 and 9. So by doing this substitution, we got it into a form that we can now anti-differentiate. All right, well, let's go ahead and just finish this off. Let's plug those numbers in. I'm going to run that up here. So I've got 1/4 times, when I plug in 9 to the 3/2, The square root, remember the half here is a square root. So the square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. Times 2 is 18. So that's 18. When I plug in 9 here, I get 3 divided by 1/2, which is 6. And then when I plug in 1 to the 3 halves and 1 to the 1/2, that's 1 either way. So I get here 2/3 plus 1. So that's 1/4 times 23 minus 2/3. That should be a 23, not a 33. Let's see, so that's 69, 67 thirds divided by 4, I think is 67 twelfths. I think. I kind of sped through the arithmetic there, so hopefully that's our value. I don't care so much about the plugging it in. That's total monkey math, right? That's just let your calculator do its thing. What's more important is to see how we got there, the steps that we did. All right, but this is the whole idea of substitution, is turning it from something we have no idea how to anti-differentiate into something that we do know how to anti-differentiate. I am going to warn you, this is going to require a lot of algebra. And in my experience, remember I've been teaching calculus for like 24 years now. Algebra is what's going to get you. The calculus itself is not bad, but the algebra is where you're going to falter. All right, so here is kind of the warm up, remember how to do this. But I want to show you a few more, and specifically, I'm actually going to dive to this next guy, which is we're going to find the integral of tangent. We're going to see what function has a derivative of tangent. But before I go there, any questions on this guy? All right. Okay, so let me clear this and let's look at tangent. So this time, let's see if we can figure out the antiderivative of tangent. All right, so as it is, you're probably like, well, there's, I don't know, how are we even supposed to attempt to do this? Right, like we know the integral of sine, we know the integral of cosine, but tangent, we don't have anything that gives us a derivative of tangent. In fact, there's only one function that even has tangent as part of its derivative. Do you remember which one? Which function leads to something with tangent? Oh, all this horrible stuff from forever ago, right? It's secant. So a couple of you guys threw that in, thank you. So the derivative of secant, of course, is secant times tangent, which this is not, has no secants. All right, well, hopefully you have learned, when in doubt, what do you do with tangent? If you're doing something with tangent, you have no clue what to do, where's a good place to start? All right, thanks, Adam. That's exactly what I'm looking for. Let's turn it into sine and cosine. Right, we can turn it into that fraction sine over cosine. All right, now, why is this beneficial when it comes to doing an integral? Well, it's exactly what we just did. It's the let's do a substitution. All right, so I'm going to let u, in this case, equal cosine of x. And you'll see why. Okay, so if we let u equal cosine of x, I'm just going to substitute down here. What's that make my du? What's the derivative of cosine? Good. It's negative sine of x. Now I'm going to put here a dx. So I can go ahead and solve for my dx here. I get that dx is equal to du, or negative du over sine of x. So let's put all this stuff in and let's start changing this. So we're going to have the integral of, I got the sine of x, but the cosine we're going to make a u. The dx becomes a minus du over sine of x. And we're in that lovely situation where the sines are going to cancel. And so check out what happens with this substitution. We end up with the negative integral of 1 over u du. All right, so by turning it into sine and cosine, it turned into a form where we could do substitution. And I did specifically choose u to be the bottom, because some of you might have gone, well, wait a minute, what if we had let u equal sine? Then the du would have had a cosine and maybe stuff's going to cancel. Well, if you run through that algebra, you're going to see that it doesn't. You're going to end up with actually a cosine squared, which is even worse than having just a cosine. So the trick to this one is just saying, well, we're going to do the substitution in the bottom. But now we can do this integral. What's the integral of 1 over u? What function gives us a derivative of 1 over u? Good, Alexi, thank you. It's the natural log. So this is going to be negative natural log of u. And we'll be good about it. We'll put our plus c. Yeah, no worries, Rigney. I figured that's what you were going for. So we're going to have negative natural log of u. But again, we need to replace. We need to get back to our x's. So let's convert that back. Let's put our u back in. So we get negative natural log of cosine of x plus c. But I'm going to do one more thing to simplify this a little bit. I'm going to take this -1 multiple and I'm going to bring it in as an exponent. That's the rule of logs. So this gives me the natural log of cosine to the -1, which of course is 1 over cosine, which you guys know as secant. So check it out. We now know the antiderivative of tangent. It's the natural log of the secant of x. Now, you probably saw that along the way I threw in some absolute values. And that's because technically back here, when we did the integral of 1 over u, it's technically the absolute value of u. I don't know if you remember that from back in the day, but I'll just go ahead and we'll set the record straight here for sure. Everybody sees it. When you integrate 1 over u, you actually get the natural log of the absolute value of u. In most applied situations, like if we were going to actually be doing this to find an area or some such thing, it's usually going to be the case that that's not a problem. Usually these things are such that the natural logs are going to be defined. But especially when we're dealing with trig functions, we know that they're very frequently negative. It's really important to put those in there. But check it out. Substitution actually got us the integral of tangent. And you can do something very similar to get the integral of cotangent. Right? For the integral of cotangent, you're going to make it cosine over sine. And then you let u equal sine of x. And if you do that, you get the integral of cotangent. I bet you can guess what it's going to have. It's going to have a natural log, but not of secant. What do you think is going to go in it?
Tangent?
Ooh, not tangent, but I like how you're thinking because secant and tangent are very related. It's the other one that's,
Cosecant?
yeah, it's actually cosecant. Remember how often, like with derivatives, like think about your derivatives, tangent versus cotangent or secant versus cosecant, they're like identical except for the fact that one's a cofunction. Well, it turns out the same thing happens here. But there's also, well, we got to have our plus C, right? And you can see this, like if you were to take, there's going to be a minus sign on here as well. But check it out. Do the derivative, natural log of cosecant, right? If we differentiate that, don't know if you remember the easy thing for logs, the easy way to remember this. It's always the thing inside goes on the bottom and the derivative of the thing on top, or thing inside goes on top. So the derivative of cosecant is a negative cosecant cotangent. And so you see here that the cosecants cancel and we're left with negative cotangent. That's why we need to throw a minus sign on there. But this actually brings me to another good point, and I think this is a good thing for us to leave with, is that when you anti-differentiate, when you integrate, it's always possible to check yourself. It's always possible to see if you did it right or not, because all you have to do is differentiate your answer. And if what you just got, if its derivative doesn't match what you started with, you did something wrong. So this is like the ultimate for someone like me. Like I hate being wrong. I hate being wrong. I guess actually more to the point, I hate other people knowing I was wrong, right? Because if I'm wrong and nobody finds out, whatever. Well, that's not true. It still pisses me off a little bit, but it really bothers me if other people know I'm wrong. With integration, I can always catch these things. I can make sure that I'm not wrong by checking the derivative, right? So remember that. You've got a great way of checking yourself. Just do a real quick derivative of your answer and see if it's the same thing as what you started with. If it isn't, oh, you made a mistake somewhere and you can go back and find it. Okay, so it looks like we're out of time. So I'm going to go ahead and end things here. Let me stop sharing the screen. Actually, real quick, any questions on this guy? Hopefully you sort of see that little trick. And this little trick we're going to pull a lot where, especially with the trig functions, if you can change the form a little bit using identities, it's going to be really helpful. So all that identity stuff from last year, when you went, never have to worry about it again after the final, false, false. We're going to use identities a lot. So, all right. So with that, let me come back here so you can all see the big of me. Anyway, so some things just to let you know. Monday, we do not have class. All right. Monday is Martin Luther King Day. So we don't have class. If we were on campus face-to-face, the campus would be locked and closed. So we are doing exactly the same thing. So enjoy the day off from calculus. I know that this day has turned into a day of service. A lot of people go out and do things. So if you are so inclined, go out and make the world a better place. Even if it's just going and collecting trash somewhere or something, little drops in the bucket, right? Anyway, so we don't have class on Monday. That also means that the next homework set is not due Monday night at midnight. It's actually due Wednesday night at midnight. So you also have a couple more days for the next homework set. So just be aware, you don't have to frantically try to get everything done on Monday. Instead, you can frantically get everything done on Wednesday, or be smart about it. Anyway, so no class Monday. That homework stuff is due Wednesday. And on Wednesday, we're going to keep talking integrals. And we'll move on to things like logs and exponents, and the trig functions, and basically just start building up the antiderivatives for things that we don't already know, and also kind of remind you of some of the important forms. Okay, so that's kind of our goal for probably the remainder of next week. So with that, I am going to wish you all an awesome long weekend and stop our recording.